Hello all, welcome back to Methods of Operations Research course. In our previous lecture, we completed our discussion on the branch and bound algorithm. And in today's lecture, we are starting a new topic, a new algorithm called the cutting plane algorithms. Actually, the branch and bound algorithm and the cutting plane algorithms have the same general structure. Both of these methods start by solving the LP relaxation of the integer program, and depending on the solution that we obtain from that LP relaxation, we include a new constraint into the model. So in the branch and bound algorithm, we try to restrict the values of the decision variables. In cutting plane algorithms, we form a spatial constraint with a methodology, and we include this additional constraint into the model so that the previous LP relaxation optimal solution will not be feasible anymore due to this new constraint, but all other integer solutions in the feasible space will still remain feasible. So the method that we are going to learn here to generate these constraints is the so-called fractional cuts or Gomory cuts. So since this constraint trims the feasible space, cut the feasible region, therefore the algorithm is called the cutting plane algorithms, and the new included constraint is called a cut. So let's get started to learn the details of this algorithm. As I said, in the cutting plane algorithm, similar to the branch and bound algorithm, we will start by solving the LP relaxation. So we will relax any integer restricted variable and assume it to be a continuous variable. Okay? And then depending on the solution, if that solution is integer, then it means that we found the optimum solution and we stop. But if that solution is not integer, then we insert an artificial constraint, and this constraint is named as a cut. This is because the name of the algorithm is cutting plane algorithm. So we are cutting something. What we are cutting is we are cutting the previous optimum solution. Okay? But while doing this, previous optimum solution for the LP relaxation. But while doing this, we keep all integer solutions. Okay? They are still feasible solutions. And after adding this constraint, if we obtain an integer solution, then that's okay, it's the optimum solution. Otherwise, we add a new cut, a new constraint, and solve it again. And we do this repeatedly, again and again, until we obtain an integer solution. In order to illustrate this algorithm, we will consider such an example. This is a maximization problem with two constraints, and x1 and x2 are two integer restricted decision variables. Initially, in the first step, we relax the problem and determine the optimum solution for the LP relaxation. So this is the feasible region of the problem, and these black spots, these black dots, denote the integer feasible solutions, and this area here is the feasible solution of the LP relaxation. And if you solve the problem graphically, we can identify the optimum LP relaxation solution to be this point. And as you can identify, this is x1 value and this is x2 value. x1 and x2 are not integers. It's 4.5 x1 and 3.5 x2. That's why this solution of the LP relaxation does not provide us the optimum solution for the original integer problem. So what do? We include a cut. For example, this is an example of a cut. You see the original constraints are this one and this one. Now we include a new constraint, which is this cut. And when we do it, you see that this triangle over here all the solutions inside this triangle are eliminated. And the previous LP relaxation optimum solution was this corner here. And we eliminated that one as well, right? So what do we have? But if consider the black dots, the integer feasible solutions, did we eliminate any one of those integer feasible solutions? No. You see this solution, integer feasible, and this solution, integer feasible, they are still inside the feasible region on the boundary. And the new optimum solution after including this constraint appears to be this corner here. And x1 value is this one and x2 value is this one. And as you see, this solution is not still an integer solution. x2 value is integer but x1 is fractional. It means that this is not the optimum solution for the integer program. We continue and add a new cut. And you see the newly included cut is this one. And again, when we include this cut, the previous LP optimum was this corner here. So we eliminated that corner together with this triangle, all the solutions here. And the new solution appeared to be this corner here. And again, you see we eliminated some solutions from the feasible region, but none of these solutions is an integer feasible solution. All black dots are still feasible. And when we solve this new problem with this new constraint, which is called cut 2, the optimum solution appears to be this corner where x1 has 4, x1 has a value of 4 and x2 is 3. And this is an integer solution. It means that we stop. This is the optimum solution. Okay, so we include such cuts, such new constraints. These are artificial constraints. They do not appear in the original model. With a procedure that we will talk about later on, we found these cuts and we include them into the model, and we repeatedly include these constraints until we obtain an integer solution. This is very important. The reduced feasible region has two important properties. First one is it does not contain the old optimum LP relaxation. You see, old optimum LP solution was here. When we include cut 1, the old one, this one, is outside the feasible region now. Okay, from this one to the other, you see the old optimum solution was this one, and with the addition of this cut, that old optimum solution appeared to be out. So the property of a cut is it does not contain the old optimum of the LP relaxation. Secondly, it contains all the integer feasible solutions. So all black dots here are also feasible here and are also feasible here. We didn't cut any one of those integer solutions. These are the two important properties of the cuts that we include. Okay, but how we can find the cut? The question is this: how we can find such constraints so that the old LP relaxation will be cut, but none of the integer feasible solutions will be eliminated. So there are different methods, different procedures to find such cuts. One of the important and earliest ones is the so-called Gomory cuts or fractional cuts. And it has a very simple idea and very simple procedure, but it's very effective. So basically we can talk about two steps. This is the very short version of the Gomory cuts. In books you can see different versions of this, but at the end it reduces to these two steps. So what do we do? First, we take a constraint from the optimal simplex tableau. Remember, we are solving an LP relaxation, and how do we solve it? With this simplex algorithm, right? So at the end of that solution, we have the optimum simplex tableau. Okay, so in that simplex tableau, we take one of the constraints for which the right hand side is fractional. Okay, we take such a constraint, and for this constraint, we express each of the coefficients of the constraint as the sum of an integer, okay, as the sum of an integer and a non-negative fraction. Okay, we will make examples, so if you don't understand by now, don't be confused, just continue and you will understand. Okay, this is just a preview of the algorithm. So we represent each of the coefficients as a sum of an integer and a non-negative fraction. Okay, there is only one way to represent these coefficients. You cannot find alternative ways, only one way. Okay, in step 2, what do? We drop the integer terms. Okay, so we represented them as integer plus a fraction, and then we drop the integer part, and we change the equality constraint to greater than or equal to. Again, remember, in simplex algorithm, in the standard form, we need to represent each constraint as an equality constraint. So in the optimum simplex tableau, the constraint that we are considering must have an equality sign. So what do? We replace this equality with greater than or equal to. So it's very easy, very simple, and when we make examples, you will understand better. So let's continue. Okay, if we solve the example problem, this maximization problem using the simplex algorithm, the first thing that we need to do, remember in the simplex algorithm, we first need to convert these constraints into equality form, into standard form. So we need to add slack variables here to make them equality. Okay, so in this example, we represent x3 and x4 as the slack variables included to these two constraints. Okay, so both of these constraints are now equality, and when we solve using the simplex algorithm, we obtain this tableau. Okay, so this is the optimal tableau. How we understand if it is optimal or not? Again, remember, in a maximization problem, simplex tableau is optimal if the non-zero coefficients are all non-negative. Okay, you see all of them are non-negative, then this is the optimal tableau. You can see the solution from this tableau. The z value is equal to 66.5, x1 value is equal to 4.5, and x2 value is equal to 3.5. This is exactly the same with the graphical solution that we obtained in the previous slides. As I said, the LP relaxation optimum value is this one. Z is this, x1 value, x2 value, x3 and x4, the slack variables are 0. In fact, the information that we have in this tableau is a set of equations. So we can write this set of equations. For example, consider this row 0. What is this set of equations? So this is the right hand side. Okay, this is the right hand side, and these are the variables. So what do we have for this row 0? Z plus 0 times x1 plus 0 times x2 plus 63 divided by 22 times x3 plus 31 divided by 22 times x4 is equal to, so this equation is equal to 66.5. So when we ignore these zeros here, we obtain this equation. From the first constraint here, again we obtain x2, okay, y it's x2 times 1, okay, then 7 divided by 22 times x3, okay, 1 over 22 times x4, equal to 3.5. And from this last constraint here, we have x1 times 0, 1 times x1, 0 times x2, and minus 1 over 22 times x3, and etc. equal to the right hand side. So we have in fact 3 equations that are written in this tableau. So the equations corresponding to the constraints in the optimal tableau can be used to generate the artificial constraints, the cuts. Remember the first step of the Gomory cut, we need to select, we need to have a constraint, and we need to represent the coefficients of this constraint as an integer plus a fractional part. So for this purpose, we need to have a constraint. And we can use any one of these equations in the optimal tableau to generate a cut, but the right hand side must be fractional. So for the selected constraint, the right hand side must be fractional. In the first step, we write the coefficients of the constraint, non-integer coefficients of the constraint, as an integer plus a fractional part. Okay, so but this fractional part, it is very important. This fractional part must be strictly positive. This is very, very important. You should be very careful about this. Okay, so let's make some examples and it will be more understandable what we try to say. Assume that the coefficient of a variable is 5 over 2. 5 over 2 is 2.5. I need to represent this as an integer plus a fractional part. So integer is 2, 2.5. So integer part is 2 plus the fractional part is 0.5 or 1 over 2. For positive coefficients, it's easy, no problem. But if the coefficient is negative, you should be careful. Why? Because the fractional part must be positive. If our coefficient is minus 7 over 3, how can I represent this? I can represent this as minus 2 minus 1 over 3, right? So this is minus 7 over 3. So I represented it with an integer plus a fraction. But this is not correct because the fraction must be positive. And in order to make this fractional part positive, what do? I write the integer part as minus 3, not minus 2. And then I write the fractional part, we write the fractional part as plus 2 over 3. Okay, so this is very, very important. Although this is also equal to minus 7 over 3, we want to write this in a way that the fractional part is positive. So for the integer part, it can be negative, positive, it's not important. But for the fractional part, it must always be positive. Okay, so while writing this, you should pay attention, special attention to this. And the thing is, there is only one way to write this. For example, if the coefficient is, let's say, minus 3 over 2, how can we write this as an integer plus a fraction? So this is minus 1 over 5. You should say minus 2 plus 1 over 2. There is no other way of writing this so that the fractional part will be positive. There is no other way. It's unique. You can write this only in a single way. So if you write it as minus 1 over 2, it's also equal to minus 3 over 2, but it is not correct according to this restriction. Okay, be very careful with this one. In the given optimal simplex tableau, we had three equations. Remember, the first one was for the objective function for row 0, and there were two other constraints for the two equations for the two constraints. We can generate a cut from the objective function from the row 0 as well. Okay, so this is the equation corresponding to row 0. Now what shall we do? We will represent the coefficients of the variables in this equation as an integer plus a fraction. Okay, so how do we do it? Let's start from the first variable, z. Its coefficient is 1. Okay, then we have 1 times z. It's already integer, there is no fractional part is 0. Okay, for the second one, 63 over 22, it is 2 times, okay, 2 integer part is 2 plus the fractional part is 19 over 22. So that when you sum up this value, it's 63 over 22. Okay? So integer plus a fractional part, and this fractional part should be between 0 and 1. It cannot be greater than 1. Okay, so this fractional part means it is less than 1, and it should be positive. What about the second one? So it is 1 plus 9 over 22. Okay, so integer plus positive fraction, and equal to the right hand side. We write the right hand side again as an integer plus a fractional part, 66 plus 1 over 2. So this is the first step. And the second step is very easy. We basically delete the integers. Okay, we have 1 times z here. So we delete that 1. Then we delete this 2 integer. We remove this 1 which is integer. We remove this 66 which is integer. So we only keep the fractional ones. Okay, so from here we have this one as fractional, and from here we have this one as fractional, and from here we have this one as fractional. The next thing to do is to change this equality to greater than or equal to. So be careful, this is always greater than or equal to. It doesn't depend on whether the problem is a minimization or maximization and etc. It is always greater than or equal to. Okay, so what is the cut that we obtain? The first term is this, the second term is this, and this is the right hand side. Okay, this is the right hand side, and then we obtain this cut here. And this is correct, this is totally correct, but instead of representing the cut as a greater than or equal to, we want to represent it as a less than or equal to constraint. And for that purpose, basically, we multiply this constraint by -1. Okay, and then what do we have? We have minus 19 over 22 x3 minus 9 over 22 x4 less than or equal to -1 over 2. The reason that we do this is to represent the constraint as a less than or equal to, because later on we will integrate this into the optimal simplex tableau to find the new solution, and for that purpose we will use the dual simplex algorithm. For that dual simplex algorithm, we want to represent it as less than or equal to. Otherwise, this is correct. This is not wrong. It is the same thing, basically. Okay, but just for further correspondence, we want to use this version. Okay, now it is time for you to test yourself if you understood the procedure or not. So please have a look at these two equations, the other two equations of the optimal simplex tableau, and please write the corresponding Gomory cuts or fractional cuts corresponding to these two equations. So you will generate one cut for this first equation, and you will generate one cut for the second one. So please stop the video at this point before moving to the next one, and write the cuts by yourself. I hope you tried by yourself to write the cuts, and you can check your answers for the first equation. The cut is this. If you found a different version in which you have 21 over 22x3 plus 3 over 22x4 is greater than or equal to 1 over 2, that's okay, perfectly fine, because it is the negative of this one. Or if you represented this like this is less than or equal to minus 1 over 2 instead of writing in this form, it's also okay, correct, okay, no problem. And for the second one, the cut should be this one, okay. Again, you can, if you like, you can move this 1 over 2 to the right hand side, or if you can multiply this by minus 1 and to have a new cut. Okay, so in fact we generated 3 cuts from the 3 equations of the optimal simplex tableau, but in cutting plane algorithm you only need one of these. We don't use all 3 cuts, just one of the cuts generated, and we will add it into our problem formulation and solve using that one. Okay, let's make an example. Write all possible Gomory cuts corresponding to the optimal simplex tableau. So this is an optimal simplex tableau. This is row 0. We have 2 constraints. S1 and S2 are select variables. X1 and X2 are original variables. This is the right hand side. Okay, we are asked to write all Gomory cuts corresponding to this one. Please work yourself on this problem. Try to write all possible Gomory cuts. You should be writing 3 Gomory cuts, and then in the next slide you will find the answers. Please stop the video at this point and try to write the Gomory cuts by yourself. Okay, so I hope you worked on the problem by yourself and you were able to write the Gomory cuts. These are the answers. Okay, so you can check your answers with this one. Basically, how do we do? For the first one, this is row 0. For row 0, z is already 1, so you can eliminate. X1 is 0, you can eliminate. X2 is 0, you can eliminate. For S1, it's 1 plus 0.25. Okay, the fractional part is positive, so we eliminate the integer part. So the remaining part is 0.25. This is already fractional. There is no integer part on it, so we keep it as it is. And the right hand side is 41 plus 0.25, so we eliminate 41 and 0.25 remains. So for the sign we put greater than or equal to. So 0.25 S1 plus 0.75 S2 greater than or equal to 0.25. As I said, while implementing this into the tableau, we will multiply it by -1 so that this sign will become less than or equal to. Okay, for the second constraint here, again we eliminate this one, and this one. So this is 2 plus 0.25. So we eliminate the integer part and the remaining part is 0.25. Okay, for S2, it's a negative fraction. So we need to write it as a positive fraction. And how do we do it? Okay, let me show it. So the result should be minus 0.25. So you go to the smallest integer than this value, 0.25, which is -1. Okay, so -1, and you write it 0.75 so that this summation is equal to minus 0.25. Then we eliminate the integer part, which is minus 1. So the remaining part is 0.75. In fact, be careful when you have negative fractions. This negative fraction 0.25 plus 0.75 in absolute values, it should make equal to 1. Okay, so you can think in that way. And for the right hand side, again we eliminate the integer part and we keep 0.25 and we change the sign to greater than or equal to. Many students forget about this while solving these kind of questions. They either forget to change the sign to greater than or equal to, or they change it to less than or equal to, depending on whether it's minimization or maximization. So be careful. And let's make an observation here. If you look at these two cuts that we obtained from the first and the second constraint, the row 0 and the first constraints, they are identical to each other. Can you see? These two inequalities are identical to each other, and it can be, and as we said in the cutting plane algorithm, we will use only one of these. We will not use two of these. So you will select randomly one of those and implement it. And for the last one, again, this is 0, integer, integer, integer. So for this one, I need to write it as positive fraction. So I will first take the integer less than this value, so which is minus 2. Then I will add a fraction which will make this 0.25 equal to 1, so which will be 0.75. Okay, and we will then eliminate this integer part. And here it's already fractional. And this is, the right hand side is 3.75 and we eliminate the integer part. So we have 0.75 as 1 plus 0.25 as 2 greater than or equal to 0.75. You see, in all of these cuts, there are no negative elements. All of them are positive. But as I said, when you are implementing this in the tableau, we will multiply them with minus 1 so that every one of them will be negative and the sign will be less than or equal to. But as I said, if I ask you in a quiz or exam to write the Gomory cut without any implementation, and if you write in this form, it's correct, it's okay. But if I ask you to implement these in the tableau and find the new optimal solution, then you need to multiply with minus 1 and implement in the tableau. Okay, so in this lecture we will stop at this point, and in the next video tutorial we will see how we can implement these cuts into the Simplex tableau and find the new solution.